We are continuing to work with polynomial division, but in this video we're going to look at synthetic division, and then we'll look at the remainder and vector theorems and how that applies. So we're going to do a little flashback to something from earlier in the year where we did synthetic substitution. Direct substitution in this first example would be where I just took 2 and I plugged it in and found the value of our function. But we did synthetic, which was where we picked off our coefficients of our polynomial. We always checked to make sure it was in standard form and that we didn't need any zeros as placeholders, and I don't. So 1, 5, -7, and 2. We made this box, we put the value of 2 right here, and then we repeated 2 simple operations, multiply, add. So let's do that. Bring down my 1, multiply by 2, and add. 5 plus 2 is 7. Now I'm back to multiply. I take 2 times 7, which is 14, and I add, which is 7. Now I'm back to multiply. 2 times 7 is, again, 14, and I add, and I get 16. And this is my remainder. So we learned that f of 2 was equal to 16. Okay, so why are we looking at this again? Because we did this already this year. Because there's something even cooler going on here. All right, so what I'm going to do is I'm going to show you that we've already done this problem in our last video. So here is the actual work from our last video that I just imported in, and I'm going to put them side by side for just a second. And what do you notice? Okay, so, well, we did long division with the same exact problem, and check out our remainder, 16. Check it out over here, it's 16. Look at that. That is our remainder, which is easier. Well, I sure hope you think that this one here is. I do. But guys, it gets even cooler than that. Check out the quotient part, this x squared plus 7x plus 7. Compare it to this right here. Right? Do you notice something? Gosh, I sure hope so. This is how cool this is. All right, let me slide this out. I'm hoping that you notice that the remainder is given, and not only that, but the first quotient part. Here's what happens. This synthetic division produces not only the remainder, but this part right here produces your quotient part, where this 7 right here is your constant. This is your x to the first, and this would be the coefficient on your x to the second. So we can just do synthetic division for certain types of problems. So this brings us to our first important theorem, known as the remainder theorem. If a polynomial f of x is divided by x minus k, so that's telling you that your divisor has to be linear. It could be like x minus 4, it could be x plus 10, okay, so minus a number or plus a number. Then the remainder is equal to f of k. We know how to find f of k. We just do that with synthetic. So this kind of shows you why you had to learn long division. Long division is great for polynomials that are bigger than a linear divisor. So if you're dividing by a trinomial or even something bigger, polynomial long division is your only choice. Let's illustrate this more now with some examples. We are told to divide this function by x plus 3 using synthetic. So first of all, here's what you need to notice. This is linear. It needs to be in the form of x minus k, and then it's your k value that goes on the outside. So here's what I always think. This is kind of like in factored form. We need the 0. Well, the 0 is, from our last unit, is always opposite of the factor. So my 0 is -3. All right, so I'm going to put this to help you keep it straight in your mind. Now we're going to set up our synthetic. 2, 1, -8, and 5. I do not need any placeholders. So I bring down, now I multiply -3 by 2 is -6. I add and I get -5. I'm back to multiply. This would be 15, add would be 7. -3 times 7 would be -21. I add and I get -16. Here is my remainder, but it's better than that. This remaining part here is actually, I'm going to give you a vocab word. This is known as the depressed polynomial. Sounds like a sad little polynomial. And again, this one is your constant. This is your x to the first. This is x to the second. And then if it would have any more to the left, it'd be x to the third, x to the fourth, etc. So I'm going to write my answer now in a cleaner format. So this is equal to 2x squared minus 5x plus 7 plus my remainder of negative 16 divided by the divisor, which was given right here. It's x plus 3. All right, that's my entire quotient. Hoping you think this is easier than the long division. Okay, we're doing another one this time. We're dividing our function by x minus 3. So again, this is in factored form. We need the 0. So the 0 would be positive 3 on the outside. I'm going to set up my synthetic. I do not need any zeros as placeholders. Oh, let me correct that. Yes, I do. It's missing a constant term, so I need a 0 at the end. So I bring down the 1, and then I multiply, add. So 3 times 1 is 3, add, and I get 6. 3 times 6 is 18, add, and I get 5. 3 times 15, or I'm sorry, 3 times 5 is 15, I add, and I get 0. 3 times 0 is 0, I add, and I get 0. And now something interesting is happening here. I have a remainder of 0, so let's just write our polynomial. So this would be the constant term, this would be x to the first, x to the second, and this one is x to the third. So my quotient is x cubed plus 6x squared plus 5x, and I don't need to write the plus 0. And notice there's no remainder, there's nothing left over. So it says, what would we call x minus 3 in this example? Since x minus 3 goes into it with no remainder, I'm going to call that a factor, right? So why would I call it a factor? For instance, 4 is a factor of 24. Why? Because 4 goes into 24 6 times and there's nothing left over. The remainder is 0. Whereas 4 is not a factor of 22 because 4 goes into 22 5 times, but there's 2 left over. There's a remainder of 2, so 4 is not a factor. So if something goes into something evenly, we can call it a factor, meaning it has a remainder of 0. And lo and behold, that's a very simple idea, but it's so important that we give it a theorem in math. We state that a polynomial f of x has a factor in that form of x minus k, a linear form, if and only if f of k is equal to 0. So if the remainder of 0, then it is a factor. We are going to use these two theorems now to factor higher order polynomials. This is a cubic function. In our previous unit, we did lots of quadratics, but not cubics. So we're told that x plus 2 is a factor, so the corresponding 0 would be negative 2. Goes on the outside, 3, negative 4, negative 28, and negative 16. And I am going to do my synthetic division. And I get a remainder of 0. But I knew I should get a remainder of 0 because I was told it was a factor. So here's what I know so far just by doing that my original polynomial is equal to x plus 2 times this remaining polynomial. This would be times 3x squared minus 10x minus 8. Okay, so this times this produces this original polynomial, right? But I'm told to completely factor this. Well, now I have a quadratic, and I'm just going to off on the side try to factor it further. There is no greatest common factor, so I'm going to jump right to my tic-tac-toe method. My factors of 3x squared would be 3x and x. Factors of negative 8 would be 1 positive and 1 negative, and then 2 and 4 and 8 and 1. I'm going to try 2 and 4. I'm going to put 4 here and 2 here. It's negative 12x, and positive 2x does add to negative 10x. So my one factor is 3x plus 2, and my other factor is x minus 4, and I'm not going to drop my first factor, x plus 2. So this is factored form. We've already learned how to multiply all these together, and if we did, we would get right back to this cubic polynomial. This is factored form because factors mean everything is multiplied. Factor literally means multiply. I can't go any further because all of my remaining factors are linear. This is a great question that you see on your screen. This time you're told one of the zeros is x minus 3, and we're supposed to find the remaining zeros. Okay, so notice that this is a 0, it's not a factor. So what value goes on the outside when I do synthetic? It is 3. It is always the 0 that goes on the outside. Pick off your coefficients. Again, I need no zeros as placeholders. So go ahead and crank out your synthetic division. Hit play when you're ready to check your answer. So you can see what I have on the screen so far. This tells me that since x equals 3 was my given 0, the corresponding factor needs to be x minus 3. And then I have the remaining polynomial. This would be 1x squared plus 1x, or just plus x, minus 20. I'm going to try to factor this trinomial here. I'll do tic-tac-toe off on the side. So this would be x squared, negative 20. Positive x is my checking term. Factors of x squared would be x times x. Factors of negative 20 are, well, I'd have a positive and a negative, and it could be 4 and 5, 2 and 10, 20 and 1. I'm going to go with 4 and 5. Once you've done enough of these, you see them. You may not even need to do tic-tac-toe on the side, especially for one as simple as this. So this would be x plus 5 and x minus 4. And I'm bringing down this factor of x minus 3. So now, if I apply, I'm told to find the remaining zeros. So to get the zeros, I need to apply the zero product property. So I have x minus 3 equals 0, or x plus 5 equals 0, or x minus 4 equals 0. So if I add 3 on both sides, I get x equals 3, subtract 5, I get x equals negative 5, add 4, and I get x equals positive 4. So here are the 3 zeros of this cubic function. Notice it's cubic and it has 3 answers. That's not a coincidence. Interestingly, we're going to eventually be graphing this, and zeros are where it crosses the x-axis. So it's crossing at 3, at 4, and at negative 5. We'll learn some more facts to figure out that this means that my function looks something like this curve. Okay, hopefully you agree with me that synthetic division is pretty cool. Feel free to reach out with questions, but you definitely need to do some practice to master this concept and keep things straight like zeros and factors in your brain.